Hello. Um, we're going to start section 11.8. Until now, we've done a lot of convergence and divergence of series, but most of the times we have dealt with only the series where all the an terms were real numbers, right? They were dependent upon n, but as we put in n, it becomes a real number. Now we are considering a series which has functions in the terms, right? So we start with power series. Let's define power series. A power series is an expression of the form Cn times x minus a the power n. N is going from 0 to infinity. Now you guys notice Cn here is some constant, right? But x is a variable, a is some constant, n is the counter which is changing. So if you expand it, when you put 0, C0 times x minus a power 0. Anything power 0 is 1, so that is just C naught. Plus when you put n1, C1 times, C1 is just some different constant, it's just a name, right? X minus a the power 1, so x minus a the power 1. And then C2, x minus a the power 2, and so on. So you guys notice in the series, each term has a function of x here. So that's why this is a different series than what we have been dealing with before. These constants, Cn's, are called coefficients of the series. And the number a is called the center of the series. Center of series. The power series may converge for some x and diverge for some other. So main goal of this chapter is to figure out for what values of x the power series is convergent and for what values of x the power series is divergent. That is our goal in this section here. Now before I define when it is convergent or divergent, let's talk about a very common example which you already know. This is a geometric series. Let's write this down. This is 1 plus x square plus x cube plus so on. When I expand this expression, sigma n from 0 to infinity x the power n, this is what I get. What kind of series this is? This one here is geometric series with common ratio equal to what? R equal to x. And if absolute value of x is less than 1, then this series converges. And converges to what? Sum would be equal to a divided by 1 minus r. What is a here? 1 divided by 1 minus x. So you notice that is written as the sum. So this functional series, you guys see this is an example of, this is x here. This is an example of a power series. If you want to compare it to the original formula of the power series, let's write that down. We said C naught plus C1 times x minus a plus C2 times x minus a square plus C3 times x minus a cube and so on. If you were to compare these two series, this is the power series definition. This is geometric series which we talked about just now. You guys notice C naught here is 1. Coefficient here is 1, so C1 is also 1. C naught is 1. C1 is also 1. X minus a, in place of x minus a, we just have x. So a is what? 0. Okay. X square, so x minus a square, x square, so a is 0. C2 is 1, C3 is 1, and so on, right? So this is an example of a power series with the values of C naught, C1, C2 all are always 1 and A is 0. The center of the series here is 0. Here we have a theorem which defines where the power series is convergent. So power series we already defined is exactly one of the following is true. So there are 3 possibilities. Out of 3 possibilities, only one is true. Let's see what they are. The series converges only if x is equal to a. So here It's convergent for only one value of x, which is what? A. The series conversely converges absolutely for all values of x. That means series is convergent for all values of x from negative infinity to infinity. Okay. Lastly, there is a r positive, so that series converges absolutely only for these values. Now, I want to define what these values are. So when I'm saying x minus a less than r, that means somewhere there is a, and I subtract r from it and I add r to it. If you take any values in this interval, okay, so this is the whole interval here. If I take any values in this interval, then the series is convergent. That is what this is saying. The series converges absolutely for these values. These values you should be visually be able to see as this. So these values means everything from a minus r to a plus r, and diverges for anything outside. So if you take anything outside here in this area, that means if x is less than a minus r or x is more than a plus r, then it will be divergent. Only is convergent in the highlighted portion of the interval. Okay. This r is called radius of convergence. You see, a is called the center and r is around it. So r is called radius of the convergence because it's like before, r units before and r units after. The center, a was center, remember? So it makes sense that we call r to be the radius. Now, notice in the first example, first result here, series was only convergent for one point, A. So there is only one point, there is no radius. So radius in this case is what? 0. In the second case, the series converges for everywhere. So R is like infinity, right? The radius of convergence is infinity. And in the last case, the radius of convergence is a particular number and you have to find it. Okay. So one more time, uh, convergence of the power theory, one of these three will be true. Either the series converges only at one point, which is the center of the series, or the series convergence for all x, then the radius is infinity and interval of convergence is negative infinity to infinity. If r is positive and series converges only for this interval x minus a less than r and diverges otherwise, then we call r is the radius of convergence, and the interval of convergence here is a minus r to a plus r. So interval of convergences are listed here also. Intervals means the set of values, set of x values where the series converges. So in the first case, it only converges at one point. In the second case, it converges everywhere. So interval of convergence is negative infinity to infinity. And in the last case, it converges only from a minus r to a plus r. So only between this part is convergent. This is your interval of convergence. Outside this interval, the series diverges.